Chemistry time again. Chemistry time again. We're going to do some gas law problems. Number 1 says, at 1.70 atmospheres, the sample of gas takes up 4.25 liters. If the pressure in the gas is increased to 2.40 atmospheres, what will the new volume be? What should I do first?
Well, we're using Boyle's law.
Good.
So we write down our equation.
Which is?
P1 V1 equals P2 V2.
And what should I do next?
Manipulate our equation.
Good, let's manipulate. So what am I trying to find out of this?
We are trying to find V2.
So
we divide both sides by P2.
Giving us
P1 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 V1 over P2 equals V2.
Okay, now
we sub in our numbers.
Okay, good. Yeah, and let's sub them in. So what should I write?
1.70 atmospheres times 2 point... Sorry, I messed up. I meant 4.2.
That's okay. 4.25, right?
Yep. Liters. Over 2.40 atmospheres. And it equals...
Volume 2.
Volume 2. And volume 2 equals 3.0 liters.
Good. And you can see the atmospheres drop out, leaving us with liters. Okay. Next one says, a balloon takes up 625 liters at 0 degrees Celsius. If it is heated to 80 degrees Celsius, what will its new volume be? What must we do first on this one?
We must change our Celsius into Kelvin.
Let's change Celsius to Kelvin. So,
We do that by adding 273.15.
so 0 degrees Celsius plus 273.15 equals 273. That one's pretty easy. 0.15 Kelvin. And 80 degrees Celsius plus 273.15 gives us
353.15 Kelvin.
good. Okay.
Now we write out our equation.
Which is
V1 over T1 equals V2 over T2.
now.
And now we manipulate it.
Okay, giving us
V1 over T1 times T2 equals V1. I mean V2.
and
Now
then
we sub in our numbers.
okay.
So we have 625 liters over 273.15 Kelvin. Multiply all that by 353.15 Kelvin, which equals V2, which equals 808 liters.
I'm sorry, you just said 808?
Yep.
Good. We can check both of these kind of conceptually by asking ourselves, does it make sense, according to Boyle's law, for the volume to have increased? Would it make sense for the pressure to have increased? Does it make sense for the volume to have decreased? Yeah, in fact, that's what we expect from Boyle's law, right? And then for the second one, if we increase the temperature, does it make sense for the volume to increase?
Yes.
Which was what happened. Yeah, it does. So good. Those are both good. Okay, that's how we solve gas law problems. Today we're going to talk a little bit about the ideal gas law. So we're going to wipe this. We're going to move to a blank area of our blackboard here. Chemistry 2, it says. Okay, so like I said, today we're talking about the ideal gas law. So let's write that down. Ideal gas law. So this is taking the combined gas law, which combines Charles Boyle's and Gay-Lussac's laws, into one, taking that and combining it with another thing that we know, which is that equal volumes of gases that are the same temperature and the same pressure have the same number of molecules. And we can measure molecules by moles, right? There's 6.02 times 10 to the 23rd molecules in a mole, or any particle in a mole. We call that principle that I just said Avogadro's principle. So Avogadro's number we know. Avogadro's principle is, you should write this down, equal volumes of gases at the same temperature and pressure have the same number of molecules. So if we know pressure, volume, and temperature, we can find the number of molecules that are in that gas. If we know the number of molecules and temperature and volume, we can find the pressure of the gas, etc. And we can do all this by this equation. PV equals nRT. That is capital P times capital V equals lowercase n times capital R times capital T. Where capital P is pressure, measured in any unit, but we have to be careful because when we get to R, we'll talk about this, but we have to be careful of the units because we use different values of R depending on the different pressure units. V, of course, is volume, and for this we must measure volume in liters. When we were doing the combined gas law, since they were ratios or proportions, it was okay to use any volume unit as long as it was the same, but for this we need to have it in liters. N is number of moles, so we could sometimes call this amount of substance, but we measure this in mole. And then R is something called this gas constant, which we have a little table up here, but R is the ideal gas constant. And like all constants, it's a constant number. And we have three different values that you need to know about. So the three different values are values of R. R equals 0.0821, let me check the units, 0.0821 liter atmospheres per mole Kelvin. So basically if your answer is in, or if your given is in atmospheres, we would use this one. We have 8.314. Yeah, 8.314 liter pascals per mole Kelvin. So if your units are in pascals, use that one. And then also this one is the one I use the most infrequently, the least frequently, is liters millimeter of mercury per mole Kelvin. And these units or these constants will be provided for you anytime you're using this calculation. If you're going to memorize one, I would memorize this one. This is the one that is used most frequently, or at least that I've seen used most frequently. And then finally, as you know, temperature, we've kind of run over, but temperature, capital T, is temperature, and just looking at all those constants, what must temperature measured be in? What must temperature be measured in? Kelvin. Just like our other gas laws. We have to have temperature measured in Kelvin. So really, this, in the realm of science education, this equation is a simpler thing to use than the proportions we were using for the combined gas law, just because we're used to handling and manipulating equations like this that don't vary over time like the combined gas law did. Additionally, using this and kind of working with the numbers a little bit, we can learn two other equations if you look at the derivations of this and where the numbers come from. We can also write these two down. Capital M equals lowercase m RT divided by PV, where capital M is molar mass, lowercase m lowercase m is mass, R we already talked about, T we already talked about, P we already talked about, and V we already talked about. So this is the ideal gas constant. This is temperature, this is pressure, and this is volume. So we can find molar mass using this equation, or using a derivation of the ideal gas law as well. And we can also use this to find density, rho. Rho equals, so rho is density, equals capital M, capital P over capital R, capital T. So rho is density, capital M, again, is molar mass, capital P is pressure, capital R is the ideal gas constant. We've talked about this 3 times now. And capital T is temperature. So this is just a derivation of the last one because mass divided by volume is rho. So we can find the density of the gas just by deriving that last one. Questions?
Nope.
If you have questions, leave them in the comments. The end.